Hello everyone, welcome to lecture 32 of the course Diffusion in Solids. So last class we started talking about the computational tools that can be used to predict the diffusion behavior, and I told you that how it is useful that if we can predict in certain cases the phases that form or the interdiffusion zone that evolves. And we talked about the CALPHAD approach, what is the fundamental of the CALPHAD, the Gibbs free energy minimization concepts, and so on. So now CALPHAD, remember, is an approach. Okay, so that is to say that okay, you minimize the Gibbs free energy, use appropriate models, and so on, and do the predictions. But then what does the prediction actually are certain softwares that have been developed to incorporate the CALPHAD approach so that you can do this phase prediction. So today I am going to tell you about some of these softwares which basically help you to which implement the CALPHAD approach and hence generate the phase prediction data or the diffusion simulations data and so on. So there are various software. We will talk about it a little bit in more detail about the software that we use in our institute. So these are the concepts covered and the keywords that are there for this lecture. So the CALPHAD implementation software, CALPHAD, as I already told, that it's a computational approach for modeling thermodynamic and kinetic properties of the material, and this is utilized by not just one software but several software tools designed for thermodynamic calculations, phase diagram prediction, and simulation of kinetic processes, diffusion, and phase transformation. So some of the CALPHAD implementation tools are Thermo-Calc, FactSage, Pandat, JMet Pro, and OpenCALPHAD. These are some very key features of these. This list is not exhaustive. It is just to give you some idea about the key features and the names of some of the softwares. All these have the first four have a commercial license. OpenCALPHAD is something which is open source, but all the commercial softwares also come with the education version as well as they come with the free version, so that somebody who is not currently affiliated to any institute can also get a feel of it. As well, when the students are learning this software, there are special students package or educational licenses available, so that you can get a lot of exposure to how the computational tools work. So in our institute, the software that we most commonly use is Thermo-Calc. So I'll give you some features about that. So it's a commercially available computational software which is used for thermodynamic modeling and calculation, and this is widely applied in material science to predict the phase diagrams, phase equilibria, thermodynamic properties of complex system, and as the CALPHAD approach implies, it uses the Gibbs free energy minimization, ensuring accurate and the reliable results. So the platform includes the multiple built-in module which allows the users to generate phase diagrams, create property diagrams like thermophysical, thermomechanical, elastic, kinetic, etc. They perform equilibrium and non-equilibrium solidification simulations, conduct advanced thermodynamic and kinetic simulations, among other capabilities. Also, Thermo-Calc can be expanded with add-on modules such as DICTRA for diffusion simulations and TC Prisma for precipitation modeling. The software integrates over 40 specialized databases for materials and thermodynamic properties, covering metals, ceramics, and more materials. So databases are key for any software that implements CALPHAD, and we will have a separate video on these databases, which are thermodynamic, kinetic databases, and so on. So let us see a little bit about the way the Thermo-Calc is structured. It provides a very user-friendly interface for researchers and engineers, while allowing advanced users also to perform custom calculations. And it is designed to integrate various models into a modular framework. So this is the software which uses databases, and the add-on modules are also available. Like I mentioned, you have DICTRA, you have TC Prisma, process metallurgy module, additive manufacturing now, which is a very hot topic, as you can say. Then property models libraries are available for material design, for steel, for nickel, for titanium. And there are software development kits also available, like TC Python, TQ interface, TC toolbox for MATLAB. Very briefly, I mean, this is no way an exhaustive list, but some of the capabilities of the Thermo-Calc. The first category is the phase equilibria. So what you can predict the amount of phases, the constitution or the composition of the phases, the solubility limits, the driving forces for phase formation can be calculated, activities and chemical potentials, phase diagrams, and potential phase diagrams, or potential diagrams. So this about the phase equilibria, you can get a lot of information about this. Then you can also get thermophysical and thermochemical properties, such as heat of formation, lattice parameters, viscosity, surface tension, thermal conductivity, resistivity, diffusivity, and so on. The kinetic coefficients, atomic mobility, tracer diffusion, intrinsic and interdiffusion can also be simulated. Then mechanical properties like yield strength and hardness, elastic properties, bulk, shear, Young's modulus, elastic constants have also been integrated in this. You can make some predictions about it. Then as I said that you have the diffusion module in this, which is called as DICTRA. It allows microsegregation during solidification to be simulated, homogenization of alloys, growth or dissolution of secondary phases, which is very important for several of the engineering alloys, allotropic phase transformations, coarsening of the precipitate phases. So various diffusion controlled processes can be simulated. Then non-equilibrium solidification properties. So the liquidus, solidus, incipient melting temperatures, segregations and shrinkage, Scheil's solidification, which is also known as non-equilibrium lever rule, that also one can try to model. Latent heat or the total heat release, fractions of solid curves, solidification path, and so on. So there are a lot of things you can do using this. So you can try out any software for that matter. Then the Thermo-Calc capabilities also include now recently added so additive manufacturing module, which allows you to take into account the melt pool dimensions, peak temperatures, viscosity, printability maps, and location specific properties or thermal history also can be evaluated. Then precipitation module, where you have the TC Prisma, which allows you to simulate concurrent nucleation, growth, coarsening of precipitates, then average particle radius, volume fraction, TTD diagrams, and CCT diagrams. So I think most of you are much more tech savvy. You can easily search on the website of Thermo-Calc. You get the free educational package, and these are the instructions you can download and basically start using. So just in the next few slides, I am going to show you an example what you can predict, and then I request you to try it on your own. You can use the free license that is available and try to work out on your own. So, you have for example, the graphical mode available, which makes the life easier for a lot of students. So, where the interface is very user friendly, so it will look something like this to you. So, you have the configuration window, then you have several guides to use the software, calculators to perform the desired operation. So, you can see here what you want to generate. Then you have resources to help you learn about the program as well. So, you can see quick start, online help, example files, and so on. Then you have something called as project window, which helps you to manage your calculations and simulations within the project, and it allows you to add, remove, or modify the calculation steps in workflow. So, then there you have a plot visualization window, which allows the outputs of or which displays the graphical outputs of calculations such as phase diagram, property trends, and diffusion profiles. So, please remember this particular lecture is not meant to be a detailed step-by-step guide, but that for that you have the software and their own tools available to help you, or there are training programs that are organized to go much more into depth. But the idea is to give you a flavor of this so that you can start exploring it on your own. Then even you have log panel and scheduler, which tells you what are the scheduled tasks that you have given, and it can even track events, give warnings and errors during the calculations. So, let us say that we try to generate a phase diagram using the graphical mode. So, you please open this software and make sure you are in the graphical mode. If you are in console mode, press the switch to graphical mode tab present below the top menu bar, and you can switch to the graphical mode. So, this is how the tab will look like. Now, choose the phase diagram template. So, you see that there are several tools here. So, you choose the phase diagram tab in the configuration window. Then you do the phase diagram generation using the graphical mode. So, basically you will see a series of icons called activity nodes. These are available in the project window. So, first step is to define the system. That means for what system you want to generate the phase diagram. So, select the database. For example, let us say we want to generate an iron carbon phase diagram. Very simple that we already are aware of. Then for that, the database that one can use is called FE-demo, iron demo database. So, demo databases have limited amount of data, which is more meant for learning. Then you select the elements. So, for example, iron, carbon, we want to select. You can also mention the composition, how much composition you want to add carbon to. Then you basically click and go next. Then what you have is something called as equilibrium calculator, which allows you to set up the conditions. So, for example, here you can see that the temperature is up to 1000 Kelvin, the pressure is atmospheric pressure, system size is 1 mole. This is up to 2% carbon that we are going to plot. And then what you want to do is phase diagram, and these are the range of the temperatures, and this thing you can on the axis you can define. And we can set the variable in different units also. Here you can change the unit if you want volume percent, atom percent, etc. you can change. Again, you can set the temperatures and compositions according to your own desired limits. Then the last is which actually allows you to set up the plot, which is called as plot renderer. So here you can go basically, you will see once you click here, you will see this kind of window where this portion allows you to specify the x-axis and y-axis parameters, define the range for each axis. So you can see here the temperature is in Kelvin, the composition is as mass percent, and then automatic scaling is selected. The limits are defined as well. Then you click this button perform to click and run the calculations. So you see that this is the kind of phase diagram that is generated. It looks to you a partial phase diagram of iron carbon. This result will appear in a plot visualization window. And then you can customize the plot, you can add titles, adjust scales using the toolbar, and save the project from the file menu. So for example, to add label, you can simply click the label. You can save as to export in PNG or in JPG format. So this is, as I said, that this is just a simple example to tell you, but the real learning you will get when you try it on your own. So that would be the thing. Then a little bit, let me tell you about the diffusion module that is available with Thermo-Calc. So there is DICTRA, it is an add-on diffusion module to Thermo-Calc that makes modeling diffusion control transformations simple and accessible. And this is based on the numerical solution of multi-component diffusion equations and the CALPHAD approach. So as I told previously also, it enables us to simulate various diffusion control processes like microsegregation, homogenization, dissolution or growth of secondary phases, coarsening of precipitates, allotropic phase transformations, carburization, nitriding, etc., interdiffusion in compounds such as coating systems, dissimilar joints and so on, post-weld heat treatment, and in several scenarios. So this requires a mobility database. So remember, that is where we will talk about this a little more in detail about this databases in the next video. But this requires what is known as the mobility data, because you want to predict the kinetics. So you need the information about the atomic mobility, diffusion coefficients, and so on. So in order, in addition to the standard thermodynamic and properties database, you need this mobility information. So this contains information about the atomic mobility of individual components in the relevant phases. For example, this again is a small demo to show you that this is how the diffusion module would look like. So you can click here, so which is the diffusion tab. Then like previous, you define a system, so we click system definer. Now you see here that this is the database which is for the phases. We use the iron demo database. Now you need MFE demo, that means the mobility database. So you need actually two databases here, because one database contains only the information about the thermodynamic properties, but the information about kinetics, the mobility in different phases, is contained in the mobility databases. So this here, this is the whole package which contains FE demo and mobility FE demo. So you can choose the systems. For example, here we have chosen iron and nickel. Then once we go to the next step, then we have to put the diffusion calculator now. And diffusion calculator, once you select, you will see this kind of a window. Then you define the geometry. Geometry is planar, let's say, and then we add the name of the region or the width of the region. So you can see this width here. The region we add here. So here. Then the initial composition profile you get is like this. Then you click on the edit composition profile. So, you then mention the temperature and the simulation time. So, let us say I want to do at 1400 Kelvin and simulation time is 300 hours. Now, in the plot renderer, set the plot axis, the axis of this graph that you want to generate, and you mention the time values to be displayed in the format T star to T1 to T2 to T final. So, at different times it can give you the simulations. Then you click on perform. So, you can see that this one, the blue line is the one which we started with, which was a simple linear variation. Then as the time evolves, then for this number of hours or seconds, sorry, then you have this red profile, and then you have the time very large in which the composition profile becomes uniform. So, depending on the type of material that you choose, the elements that you choose, the time which it takes to smoothen or the evolution of this will be different. So, some of the challenges in the CALPHAD predictions, these predictions become more challenging as the systems go more complex. That means, when you have multi-component alloys with multiple phases, because there the number of phases become more, then the data should be available in different phases and so on. Then higher order interactions between components make thermodynamic and kinetic modeling intricate. So, that intricacy is there as the complex system becomes more complex. Then the accuracy of CALPHAD prediction is highly dependent on the quality and comprehensiveness of the underlying databases. So, the databases must be powerful or the comprehensive enough to include the most reliable experimentally validated data for all relevant phases and interactions. Limited or missing data for specific systems can lead to uncertainty in predictions. So, for better results, you need model accuracy. That means high quality databases are crucial for reliable predictions. You need continuous updates, because if some new experiments have taken, some information about the new phase has come, or new data has been computed, then it should be updated in the database. And then the validation, cross validation with the experiments and advanced simulations ensures further reliability. Here are the references from which some of the information used in this slides and the data presented has been taken. So, we will talk about the databases a little more in detail in our next video. So, till then, thank you.